Okay, and I think we can reconvene with this session on time. And it is my pleasure. I hope you're all kind of waking up now, so I just make a big wave. It is my pleasure to introduce our next speaker, who is talking about magnetic phase diagrams and helicity control of reverse modes in ferromagnetic nanotubes. And the talk is given by Oscar Iglesias of the University of Barcelona. So please go ahead.
Okay, thank you, Naomi, for the introduction. And today I would like to present this talk on this session on novel functionalities. And the talk is going to be based on novel functionalities, I think, of ferromagnetic nanotubes. And I will show you some results regarding the different magnetic configurations that can be achieved in magnetic nanotubes when properly tuning the exchange and dipole interactions in between the spins forming the tube, and also show you how this affects the reversal mode of these nanotubes. The results that I'm going to show you are a collaboration over the years with a group of Johan Restrepo and Hernan Salinas in Colombia, and I refer to these two recent articles for the results, more details. So first thing is just to, instead of giving an introduction on nanotubes, which would take me kind of half an hour, and I think that all you know what is a nanotube, nanowire. Will only mention how to obtain a nanotube, which would be the object of study of what I'm going to talk today. One thing, one way to get a tube is just from a general lattice, like this one in here, or graphene, or whatever. You can roll the tube following some direction. In our case, we will roll them from a square lattice along a diagonal, and then you get this kind of zigzag nanotubes with different layers, having different layers with n atoms per layer, and n zeta would be the length, will be characterizing the length of this nanotube. Why zigzag nanotubes? Okay, this would lead us to another topic of the talk, but let me tell you that rolling the tubes in different directions would give rise to different configurations also, right? So the basis of the study are here. I'm not going to enter into details, only tell you that these will be results of Monte Carlo simulations on an atomistic model of the nanotube, in which the S's here represent the spins sitting at the lattice nodes, and there will be two competing interactions, mainly the exchange interaction, which is short range, and then the dipole interaction between spins. These spins can be thought of as atomic spins, in the sense that you may roll a thin film in order to form a continuous thin film in order to form the tube, or you can think that these spins represent giant spins associated to a macromolecule that has been deposited, or a nanoparticle that has been deposited on the surface of a cylinder. Important parameter here will be the interaction ratio, gamma, which gives you the strength of dipole interaction as compared to J. When we study the reversal modes, we'll have to introduce the Zeeman coupling with the magnetic field. And in order to study the magnetic configurations, we use linear temperature decrease of from high temperature, and also an annealing in order to obtain the ground state configurations of the system. The first thing that we can study is how the magnetization varies as a function of, for a given nanotube radius and length, without varying them, how the varying the competition between dipolar and exchange interactions, as you keep increasing dipole interactions, demagnetization of the tube varies, and you see that when exchange dominates, it orders ferromagnetically, and when dipolar interaction dominates, demagnetization becomes zero, and in the middle you see intermediate states with some intermediate magnetization. From the peaks of the susceptibility hit and from the specific hit peaks and the susceptibility peaks, we can see also that there's a critical temperature for ordering, which is supposed to happen in between the paramagnetic and one of these ordered phases here. And you see that this critical or pseudo-critical temperature, because here we're dealing with finite size effects, varies with the coupling constant gamma. And there are 3 regions of characteristic variation, which now we will be studying in more detail. In order to better characterize the order parameter associated to these phase transitions, we have found that vorticity instead of ionization, as usually employed for other studies on skyrmions and so on, characterizes better what happens when we lower the temperature from high to low temperature. We see that when dipole interaction dominates, the vorticity goes to 1, which indicates the formation of vortex states. And when the ferromagnetic interaction dominates, dipole interaction is low, then the vorticity goes to 0. And in between, again, we see intermediate states, the nature of which we're going to characterize in the following. For this range of intermediate values of the coupling parameter, when we look at the magnetization components, we see that for small gamma, where exchange dominates, the spins point along the tube direction, whereas for high gamma, the spins have a component which is tangent to the surface with no radial and no axial components, which is typical of vortex structure. However, for intermediate gammas, where the two interactions compete, we observe a progressive reduction of the zeta component and an increase of the azimuthal component, which are now we are going to look into more detail. So it seems that the vorticity parameter helps us in order to understand what is the general phase diagram for a given radius and length. What we see is that the spins order ferromagnetically for low gamma, forming a perfect vortex at higher gamma, but in the middle we see this kind of helical structures in which the spins tend to follow the helix in which we have folded the lattice. So in order to better understand this, we can see here what's the angle that the spins form as a function of across the tube length as a function of the interaction, dipole interaction parameter. And we see that we go from ferromagnetic states, which have all spins aligned, to spins aligned at 90 degrees here, forming a complete perfect vortex. And in between, we see these helicoidal kind of structures characterized by intermediate values of the angle theta. Then we can also study what happens when we elongate the tube, the length dependence, which we see here as a function of the number of layers of the tube. For the magnetization and vorticity, what we see is that for small gamma values here and here, when exchange dominates, there's an abrupt transition from the vortex to the magnetic state. So the helicoidal states are not favored. Whereas for large gamma, dominant dipolar, we see a vortex-like state that dominates at all lengths. And again, in the middle, we see an intermediate values of gamma. We see that again, helicoidal states form. So picking up all these results, we can build phase diagrams for different values of the dipolar coupling to exchange parameter. And we are able to determine the different regions, lengths and radius of the tubes for which the ferromagnetic vortex and helicoidal intermediate states, metastable states, can be formed. And we see that as we increase the dipolar interaction, the vortex are favored, whereas when ferromagnetism dominates this area, extends to much wider areas of the phase diagram. And in between, there's an area for all lengths and diameters of the tube in which these helicoidal states are stable. These are finite tubes. Here you can see some examples of configurations ranging from pretty narrow tubes, changing the length. You see that there's always a cap of spins that try to form a vortex. There's a ferromagnetic area, and the extension of this cap of vortex states depends on the radius and also on the length of the tube, if you compare here from here. If the tube becomes very wide, wide diameter, then the vortex is formed completely. In order to better characterize this, we thought of, we can see here, for example, the comparison between the calculations, these two lines here, the results of the simulations, and then the comparison between different states. A mixed state, which would be formed by a ferromagnetic part, and vortices of extension lambda at the ends, which is a theoretical state, trying to describe what happens in the simulations, and also a state which is characterized by quasi-uniform orientation of the magnetization. Let's say all the spins forming an angle theta with respect to the tube length. And what we see here is that this kind of mixed state description of what happens is a very good description for precisely for the values of gamma close to the regions where we see the formation of helicoidal states. So it seems that these mixed states are a good way to describe the simulations. However, notice here that the differences in energies between the simulated annealing results from the computations and states forming a perfect vortex, or these ones, is very tiny, which means that in this region, high metastability would allow us to go from an helicoidal state to a vortex state or ferromagnetic state, depending perhaps on the history we submit the sample to. Here, I don't have time to go into on how this description of vortex states can be done. It's just a minimization process based on numerics, and allows you to study how predict which is the region in which you would find this metastability of helical states formed for any tube length and radius. And now let's switch to the reversal mode dependence on the gamma parameter. Now let's take a nanotube, this standard one, and let's study what happens with the reversal modes along the hysteresis loop. We see that for small gamma, when the change dominates, the square loops are the loops are square, which indicates the Fourier reversal, and we see that the corrosive field decreases with when increasing the dipole interactions. For intermediate gamma, for example, here these red curves, what we observe is that due to the competition of these interactions and due to the presence of these metastable helical states close to remanence, variation in the inversion modes from run to run occur, and when we are averaging over 30 realizations, we obtain these strange loops here. For higher dominant dipole interactions, the reversal proceeds according to the formation of vortex states that are the ones that form at remanence. And this can be clearly seen here by looking at the evolution of the vorticity with the magnetic field along the hysteresis loops. So in order to understand this, what happens for this range of gamma parameters in which the helicoidal states are the ground state configurations, we run 100 additional modes, runs, simulations to see, to realize that depending on the different state with which the simulation started, you can have hysteresis loops with low corrosivity, high corrosivity, or two mixing reversal mechanisms at both branches with a rate that depends on the tube length and also on this parameter gamma here. You see here that on this Q1 mode of low corrosivity corresponds to the formation of a vortex at remanence, whereas the high coercivity mode corresponds to the formation of two vortex walls that propagate and confront each other, and this is the reason for the high stability, for the high coercivity in this mode. So the question is, can we control the reversal mode by changing something, changing the conditions at which the starting configuration of the tube before the loop is considered? And the answer is yes. And how? Then we thought that changing the initial configuration of the tube before the hysteresis loop is measured can drive the different two modes. If initially we prepare the tube such that two vortices are formed with the same chirality, like in this configuration here, and a central ferromagnetic part is initiated, as in here, you see that the evolution is following 100% times the low coercive field mode. Whereas if we prepare the nanotube, as in here, with vortices with opposite chirality, then we induce the reversal by the high coercive mode. So we have a way to tune high or low coercivity in the same tube by tuning the fine-tuning the initial condition, especially the chirality of the vortices that are formed at the ends of the tube. This can also be studied for longer tubes, for 820 in this case, and we observe the same phenomenology, although in this case, the Q1 and Q2 modes happens in a different proportions. And to make the story short, we see that in this case, for longer tubes, preparing the tubes with the same chirality at the ends, we achieve 100% reversal through the low coercivity, and while preparing them in opposite chirality vortices, we achieve the high coercivity reversal mode 100% of the times. So the efficiency of the chirality tailoring depends on the tube length and even on the number of layers that you have. Similar results can be obtained by micromagnetic simulations. Of course, I don't have time to show them in this talk, and just to tell you that micromagnetics agrees with the results also. And I will leave the conclusions for you to read, highlighted in red, the main keywords and messages to take away. Thank you for your attention, and that's all. Open to questions that you may have.
Thank you very much. Are there questions? Again, please, if you have questions, write them in the chat. And maybe, yes, okay, there is a question from Carlos, Juan Carlos. In nanometers, what is the diameter of nanotube and nanotube wall thickness considered?
Well, here unfortunately we cannot go to realistic diameters when dealing with atomistic simulations, because the number of entities to be simulated with dipolar interactions, you know, it's they are long range, are difficult to tackle. You saw typically these tubes would have 8, 16 lattice lengths in diameter, and length up to 64 lattice parameter lengths. But this can be scaled up using micromagnetic simulations, as I told you. All these energies can be scaled up as long as you respect the aspect length ratio of the tube. So I think this can be extrapolated to longer tubes.
And we have a second question from Moxana.
Yeah, sure.
If this is not a numerical experiment, how would you prepare tubes with the same or opposite chirality at the end?
I was expecting this question. In fact, this is the big question, right? How do we manage to experimentally first to synthesize the tubes? I mean, there's experimental realizations of curved geometries nowadays. So I think that rolling up a ferromagnetic layer into a tube shape, of course, not with the thickness of one atom, it's not easy. I don't have a proposal, right? I mean, I'm sorry, Jan, I cannot answer this question. I'm just exciting experimentalist to reach this. I mean, maybe just if we're able to apply proper magnetic fields or currents to the end of the tubes, we can fine tune the initial configuration of the tubes one day. I've seen during the sessions of these novel functionalities, we have seen many, many nice experimental achievements along this way. But okay, for now, this is computational experiment. I'm sorry.
No, that's okay. I think that has to come both ways, theory and experiment.
Yeah.
Especially with those questions. Okay, thank you very much for the talk. And we are perfectly on time